All right, today we're going to do 4.5. This is the last section of chapter 4, and this is going to deal with rational functions. Now, I'll get to what rational functions are in the more technical sense and how we deal with them and graph them and plot them and what you can do with them. But simply put, a rational function is going to be a polynomial divided by a polynomial. And we're going to cover the first part of this is going to be a lot of definitions, so take your time. If you need to pause it and rewind it or pause it to get a few notes down, go for it, because this first part is going to be very definition heavy. But we'll cover the asymptotes, vertical, horizontal, and oblique, which oblique you may have heard referred to as slant, and then actually how do you graph these functions, things like that. So specifically, a rational function is of the form p of x divided by q of x, where p of x and q of x are both polynomials. And to no one's surprise, you can't let q of x be equal to 0. Now it says specifically here that it's cannot be identically 0, which is a fancy way for saying just don't let it be equal to 0. If you think of a polynomial with different roots, that is a non-identical 0 function. And what that means is just it equals 0 in 1 or 2 or so on places, but it does not equal 0 at every place. That's what it means to be identically 0. If a function was identically 1, that means it's just 1. And because of the way rational functions are written, or constructed, the domain is going to be all real numbers because it is a polynomial divided by a polynomial, except polynomials have roots. So the roots of the denominator, which is where it equals 0, are excluded from the domain. So that's one key thing to keep in mind here. Domain will be all real numbers except where the denominator is equal to 0. Now a vertical asymptote is the line x equals c. And that's very important that it is x equals. Vertical asymptotes are always x equals. Horizontal are specifically x equals a number, and horizontal are y equals a number. And the whole point of a vertical asymptote is it identifies a place in the function where the domain is excluded. So like if we take a look here, these are all places where roughly at 2, you cannot plug in, that's a value that you can't plug into the function. So basically what we have going on here is just x cannot be equal to 2. So if x cannot be equal to 2 in the domain, then x equals 2 is a vertical asymptote. And simply put, VA, vertical asymptote, SA for slant asymptote, or OA for oblique asymptote, and then just HA for horizontal asymptote. That's the easiest way to write these. But notice the key thing about vertical asymptotes, you can never cross them. And apparently I can't spell cross either. And that's going to be a very key thing. You can never cross a vertical asymptote. Notice with these, domain goes up towards infinity, or sorry, range goes up towards infinity on both sides. So this is just saying that as you get closer and closer to 2, so like you could plug in like 1.99 or 2.01, stuff like that. You get really close on either side, but you just can't plug in that value. And it can they can both go up towards infinity, both go down, or you can have one go up and go down. And the way you would test to see that is typically you would just pick a point close. Like I said, you could pick like 2.1, and then you could see what happens. You go, oh, okay, well, if it's 2.1, and then you pick 2.01, and you go, okay, well, it started going up, then you know that it needs to keep going up. Or like on this side, you pick 1.9, and it's like maybe here, and then you pick 1.99, and you're down here, so you know how to draw your graph from those points. Horizontal asymptotes are y equals a number. So horizontal asymptotes are a little bit different. Horizontal asymptotes act more as guides, and the graph of a rational function may intersect a horizontal asymptote, more specifically near the origin. But that's the key difference. Vertical asymptotes you can never cross. Horizontal ones, occasionally you'll cross. And so here's 3 examples, 2 of which the function actually crosses. And the first one, it actually never crosses. So this function looks very similar to like if you had, I don't know, something more along this line, where you had a vertical asymptote that was guiding, and you had a vertical asymptote that you couldn't cross and a horizontal asymptote that you also could not cross. Versus this one where you notice the graph, it crosses up over it, but then it's almost kind of like a magnet. It goes away from it, but then it slowly gets pulled back down towards it. Versus over here, it doesn't cross it, but it gets kind of pulled towards it. Horizontal asymptotes are as you go towards positive and negative infinity with your x values, basically as they get larger or smaller, what does the end behavior look like? And this is kind of like the end behavior idea for rational functions. So you just want to keep that in mind when you're looking at it. And then this one would be like if you had close to like a vertical asymptote here, and then maybe you had a vertical asymptote here. And so you can see that these asymptotes guide your graph and how it should be shaped. So next thing to do would be the oblique. And then some people don't like using the word oblique, so they just say slant. But slant, it makes sense because, well, it's a non-vertical, non-horizontal. So if it's non-vertical and non-horizontal, you end up with something like y equals mx plus b. So a oblique asymptote is going to be very similar to a horizontal asymptote, except the difference is this is almost like the end behavior. This is a better end behavior guide for functions that don't get bounded towards a number. They're just unbounded and just continue on and on. So, oh, and one thing to go back to here. You could cross the asymptote. Vertical are the only ones that you cannot cross. But eventually this asymptote only approaches from one side. So it'll cross it. It might cross it a couple of times, but what happens is once it crosses it once, it will never cross it again. Well, I just contradicted myself when I said that. Eventually, it won't be able to cross it anymore. Let me be a bit more correct in my verbiage. But so here's an example. Actually, here's, again, 3 examples. And you can see that as this function goes towards negative infinity, it just kind of hugs this orange line. But once it gets here to 0, it's almost like there's a vertical asymptote here. So this one, it has to hop over to the other side for the vertical asymptote, and then it just goes on like that. This one, very similar, except it's a lot more dramatic, the turnaround here. So this one, it doesn't actually cross it, except up here, it looks like it's getting ready to cross it. And then this last one, there's no vertical asymptote, so it just kind of goes through here, and then just goes like that. So that one's actually pretty nice and easy to deal with. Now, asymptote notation is very specific. We use this little superscript like where an exponent would go. And so you read this as x approaches c from the left. Because think about if you have your numbers here, you have -1, -2, 0 would be here. You'd have 1 and 2. If you approach a number from the positive side, that means you're approaching it from the right. If you're approaching it from the negative side, you're approaching it from the left. So if you just think about like a number line or the way your graph works. Now, so if you see x approaches c and then a minus, you're saying x approaches c from the left. Which, to go back here, if we use this first graph for example, as x approaches c from the left, the function approaches positive infinity. Or so our value for c would be 0. So as x approaches 0 from the left, the function goes towards infinity. And then as x approaches 0 from the right, the function goes down towards negative infinity. So that's just a little bit of the specificity. Now, notice I couldn't say for this one, as x approaches 0, the function approaches positive infinity or negative infinity. You can only use this one if it's behaving the same on both sides. Now, notice it says both sides. Beforehand, though, we've described x approaches infinity. This is not implying that you're approaching both sides of infinity, because implying that there are two sides to infinity implies that it ends at some point. It doesn't. So all this is saying is take into account that x is approaching infinity. You always assume that you're going towards infinity. Just because you don't say as x approaches infinity from the left, you're approaching infinity. So of course, this is going towards positive infinity. This is going towards negative infinity. So you're always going to have to approach infinity from the left. So it just kind of gets left off. So, but if you're approaching a number, keyword C is a number, and it's working the same on both sides, then you can just write x approaches c to make it a bit easier. So if we look at the first graph, so you can read it as x approaches 2 from the left, f of x approaches negative infinity. Or you can read it f of x goes towards negative infinity as x goes towards 2 from the left. Reading it either way is the same thing. So this is interchangeable with this. Typically when we're talking about infinities in this case, we'll tend to write it the way that these are all written. And again, the nice case here is shown that g of x goes to negative infinity as x goes to 2. So on the left and the right side, it's approaching the same infinity. So you don't have to write a plus or a minus or things like that. And then this one has sorry. This one is slightly different because this time h of x is approaching a number as x goes towards negative infinity. So Here, as h of x, as you keep going out to the right, it's going to approach this horizontal asymptote. So you're going to wind up at a point where it's just going towards a value versus going towards, or just continuously growing and growing and growing. This one is growing, but it's going towards like 1.9, 1.99, 1.999, just stuff like that. It just gets smaller, or larger and larger, or smaller and smaller, but in a much more minuscule way. It's getting closer to this value, not just blowing up. And so when we talk about what is the equation for a vertical asymptote, it's always just x equals c. And it's only a vertical asymptote. Now, it's a if and only if, which means you can read the statement left to right or right to left, and it's still true. So the vertical line x equals c is a vertical line, or vertical asymptote of f if and only if c is a zero of the polynomial q. But you could also read it c is a zero of the polynomial q if and only if the vertical line x equals c is a vertical asymptote of f. So if you know it's a vertical asymptote, you also know that it's a zero of the denominator. If you know it's a zero of the denominator, then you know that it is a vertical asymptote of the function as well. So for these three, we're going to find the domain, and then we're going to find the vertical asymptote. Typically, it's vice versa from what I said, because once you find the vertical asymptote, that's kind of just signaling to you, okay, what's the domain got to be? So if we start with the first one, all you do to determine your domain is you take the denominator. So in this case, it's just x plus 2 equals 0. Or it's just x plus 2. And you set it equal to 0, because you want to know where is the function going to just not work. And so in this case, just subtract 2 to both sides. And so then you get that x is equal to negative 2. Which, remember, I said the equation of a vertical asymptote was always x equals a number. There you go. There's your vertical asymptote of f of x. Now, if you look at these, or I should say the second one, this one you're going to have to factor. So sometimes they'll be just as easy as a, but other times you might have to do a little bit more work. So now we have where the vertical asymptote is. And then remember I said the domain is just all real numbers except where this vertical asymptote, or if there were multiple, where the vertical asymptotes occur. So the domain of f of x is going to be from negative infinity to negative 2, and that's going to union with negative 2 to infinity. And so if there were multiple vertical asymptotes, you would have multiple unions of intervals. So like what this says is, if you have your graph, and I don't know exactly what this one's going to look like. Oh, whoops, it's negative 2, not positive. You think about it as like a number line. So here's 0, 1, 2, 3, negative 1, negative 2, negative 3. And of course, this will keep going either way. This would be a open circle. And then everything else would be included. So you could pick values of negative 2.1, negative 2.000001, negative 1.9. You just can't pick negative 2. That's all it's saying. And so just to be aware of how this one would work, this is what you're saying, is wherever this occurs in the domain, then there's a vertical asymptote there, unless it's removable, which we'll get to removable with part C. Now, what if we look at this one? All right, x squared plus 2x minus 15. Set that equal to 0. All right, what two numbers multiply to get me negative 15? And add to get me 2. All right, 15 and 1, neither of those are going to work together. 3 and 5 are 2 apart. Which one needs to be negative? I need 3 to be negative because I need this number to be positive, and whatever sign you need, you give that to the larger number. So I need this to be positive, so 5 gets to be positive, 3 gets to be negative. If this had been minus, then it would have been minus 5 and plus 3, sorry. So this factors to x minus 3 and x plus 5. And then if you set both of those equal to 0, you get that x equals 3 and x equals negative 5s. Negative 5, not 5s. There's only one 5 here. And again, these are your vertical asymptotes of g of x. So then what we do is, after you factored it, you always write in the denominator. You use check. So we have x minus 3 times x plus 5. And then x squared plus 1 stays in the numerator. Now, x squared plus 1 does not cancel with anything in the denominator, so we're okay. If we could factor the numerator, we would. And if it canceled with something, that would create a hole in the graph, because that would be a removable discontinuity. And we'll see that in one of the examples coming up. And so then the domain of g of x will be, so negative infinity to, remember these go in descending, or from descending to ascending, so smallest to largest. So negative 5, and then we'll union negative 5 to 3, and then we'll union 3 to infinity. So that's your domain. And I recommend for some of these, if you want to see how they work, go to a website like Desmos and use their graphing utilities, and you'll be able to see these points that are being excluded from the domain. Now, remember I said we always look at the denominator first. And here's the reason for that. So I have x minus 1, set that equal to 0. Solve over, I get x is equal to 1, and that's my vertical asymptote of h of x. Now, if we go to the numerator, notice I have x squared minus x. I can factor an x out of the top. That leaves me x times x minus 1 divided by x minus 1, which those reduce and cancel each other out. So this only leaves us with the function is x. And if you look at that, you just go, well, it's just h of x equals x, so I don't have anything to exclude from the domain. You always look at the original. You don't go back to, or you always look at the original, not the reduced, for your domain. So when I do this, domain of h of x, it's going to be negative infinity to 1 union 1 to infinity. And so with that, even though you look at this and go, well, it's just x, why would I not just say the domain's all real numbers? It's because of what it was before you reduced it. H of x is this function, It just also happens to reduce to this. And in this original one, if you plug in 1, you get 0 divided by 0. So you have to be careful of that. So then how do you find horizontal or oblique asymptotes? So I already mentioned the slant asymptote requirements. The degree of the numerator has to be exactly 1 higher than the degree of the denominator. Now, the way that I tend to do this so if you think of your polynomials as this, so f of x is going to equal a sub n times x n plus stuff. And then that's going to be divided by b sub m divided by x sub m, or times x sub n plus stuff. The reason that I just write stuff is because I only care about the leading coefficients of the highest power. Because remember when we talked about in behavior, it was the leading coefficient and the highest power that determined all that. Same thing here for the horizontal asymptotes. So if n is less than m, which means the denominator has a larger exponent, then y equals 0 will be your horizontal asymptote. So if you have x squared plus, I always use this example, x squared plus a million divided by x cubed minus like 30,000. So you look at this initially and go, oh wow, the denominator is at a major disadvantage because it's starting out with being subtracted, having 30,000 subtracted off, and the numerator is adding a million. Eventually what's going to happen is that numerator will fall behind, because just because you add a million, eventually I'm going to be cubing numbers like a million. So if I cube a million and subtract 30,000, that's eventually going to win out over squaring a million and adding a million. So this one has a horizontal asymptote of 0, because as these numbers get larger, or as you go towards negative infinity or positive infinity, these are still going to get or go towards 0. All it's going to affect is if you go towards positive or negative infinity, that's just affecting which side are you approaching 0 from. If they're equal, and again, this is a n times x to the n plus stuff divided by b sub n, or m, times x to the m plus stuff. If they're the same power, then the horizontal line y equals sorry. If they have the same power, then the horizontal line created by y equals the leading coefficient in the numerator divided by the leading coefficient of the denominator, that will be your horizontal asymptote. So if you have 3x to the 5th plus 1,000 divided by 7x to the 5th minus 20,000, your horizontal asymptote is going to be y equals 3/7. This is the HA. So VA is short for vertical asymptote, HA for horizontal asymptote, and typically I'll write SA for slant asymptotes, or you can write OA, whichever works for you. If the degree of the numerator is equal to the degree of the denominator plus 1, which is another way of saying the degree of the numerator is 1 more than the degree of the denominator, or sorry, Yeah, that's right. My brain went stupid for a second. Then you'll have the slant asymptotes. Or a slant asymptote. I should not say asymptotes. The only thing, you're not going to have two horizontal asymptotes or two oblique asymptotes. You can have multiple vertical asymptotes because you can have multiple places where it's discontinuous. But the horizontal asymptotes are determined by a single, or can only have one value per function. And it's because of how they're made, because we're looking at the leading coefficient and the highest power. So if n equals m plus 1, which means like, for this one, you could do like x cubed plus something divided by x squared plus something. Then you would be able to find through long division or synthetic division if it was just x plus 1 or x plus stuff in the denominator. You could use synthetic and that would speed the process up. But if the degree of the numerator is greater than the denominator by more than 1, then there are no horizontal or oblique asymptotes. These are the functions that just go off without any real, not that they don't have real in behavior, but they don't have a predictable in behavior where you can use a oblique or horizontal asymptote to figure out how to sketch it. So we're going to take these and we're going to find the equation for the horizontal asymptotes or oblique asymptotes, whichever. So starting with number 1. First thing you always do is identify what your leading coefficients of the numerator and the denominator are. So in this case, they're both 1. Now we need to compare n and m. So remember, n is the degree of the numerator. So n is equal to 2. And m is also equal to 2. So these two are both equal. If you go back to the chart, you would see that this means that your HA is equal to the ratio of the two leading coefficients. So the horizontal asymptote for f of x is going to be y equals 1 over 1, or just more simply, 1. So look at the powers and then go back to the chart. All right. Now again, just to make this a little bit easier, if you want to, you can write this as 1. And so n is equal to 3 and m is equal to 2. So now you can either write it as n is equal to m plus 1, or I prefer to say, and you don't have to write all this out, degree of the numerator is exactly 1 more than the degree of the denominator. So that's the way I would remember it verbally. I don't typically tend to remember it as n equals m plus 1. I remember numerator degree is exactly 1 more than the denominator degree. So now the question is, how do I find the slant asymptote or the oblique asymptote, whichever you want to call it? To do that, we have to do long division, or long polynomial division. So, like before, x cubed divided by x squared, because we pull from here, that's equal to just x. So if I multiply these, I get x cubed plus, notice I actually get plus 9x, so these don't actually line up exactly. Now I'll switch their signs because I'm subtracting. And this is going to leave me with negative 7x. And then I'm going to go ahead and bring down the x squared first, because I always need to be, when I'm addressing these, I need to address the next highest power available. Even though negative 7x is all that we were able to subtract from the two functions, x squared is still the highest power that is there. And so then if I do that, I get x squared divided by x squared, which is just 1, so plus 1. So that's going to give me 1, or sorry, not 1. That's going to give me x squared plus 9. But notice plus 9 doesn't go there, so I can't really combine those two. So I have to bring down this 2. And this is going to give me, because this will become negative, this will become negative. So I'll get negative 7x minus 7. And now I want to show, because I didn't do this before, so g of x, or so this is going to be equal to g of x, because that's all I did. I did division, so this is the same function. So this is equal to x plus 1 plus negative 7x minus 7 divided by x squared plus 9. Because if you think about, like, let's say we did 101, and that was divided by 10. That's going to go in 10 times with a remainder of 1. Let's use 111. Just because that way it'll be distinguishable. That goes in 11 times with a remainder of 1. So 111 divided by 10, I wrote it too close. Sometimes if I write it too close, I can't overwrite those. So 111 divided by 10 is equal to 11 plus 1 over 10, which would be 11.1, which you know that would be true regardless. So when you do it with polynomials, it's the same way. It's what did you get as your result, add on to the remainder divided by your divisor. So to get the horizontal, or sorry, to get the oblique asymptote, so the oblique asymptote is equal, or is, I should say, is y equals x plus 1. We drop all of this stuff for the, you drop the remainder for the oblique asymptote. And again, this will just give you a guide. And my recommendation is plot g of x, but also make sure you plot y equals x plus 1. And when you do that, you'll see two different lines, and you'll notice that the graph of g of x does follow the way that the graph of x plus 1 a little bit. Now, if you're wondering why I have both of these on the same page when the other two took a decent amount of work, notice these. So what's the highest power in the numerator? 4. What's the highest power in the denominator? 6. So that means we have n is actually less than m, and because of that, you have a horizontal asymptote that is simply y equals 0. And that's all you have to do if the degree of the numerator is greater than the degree of the denominator. So, nothing much to that one. If we come down here, n is equal to 4, and m is equal to 2. Now in this case, we have that n is greater than m plus 1. Because remember, if it was equal to m plus 1, that was when we had the slant asymptote. Now it's greater than by 2. So that means there are no horizontal asymptotes or oblique asymptotes. So these are the ones that provide the least amount of challenge in terms of what do you write. All the work is just looking at the powers and comparing them in this case. So make sure you have this list down. I would recommend maybe just make a small little box in your notes, and you don't have to include all the words, but I would mainly focus in on the n is less than m, n is equal to m, n is equal to m plus 1, and n is greater than m plus 1 for your indicators. And then once you have that, you can go through and find all of these, or in other problems like it. Then it just becomes kind of like a quick reference guide. You don't have to constantly be going back and going, okay, well, which one is which? If you just break it down to those 4 things, it'll be really easy. And then lastly, how do you graph rational functions? First things first, factor the denominator and figure out the domain. Because you need to figure out, 1, what's the domain so you don't plot any points that aren't actually there. And that also gets you your vertical asymptote. So you're helping to already guide the way the graph is going to have to go. And typically you want to factor the numerator as well after you factor the denominator. Remember with the x squared minus x over x minus 1, that ended up actually reducing, and the x minus 1's actually canceled out. But because of what the original function could not have in the denominator, you have to respect that whenever you have reduced something down. So if things do cancel, those appear as holes in the graph. So you just draw the open dot for that. Yeah, so step 2, I kind of got ahead of myself. You factor the numerator, and typically after you cancel stuff, that's when you technically identify if there are holes in the graph. Check the remaining factors to determine the vertical asymptotes. So then compare the numerator and the degree of the denominator to determine your horizontal or oblique asymptotes. And if there are any, figure them out and then plot them on the graph. Determine your y-intercept, which is just plug in 0. Keyword or key thing is if 0 is in the domain. If it's not, skip step 5. Step 6, if you've already factored the numerator, you've already determined if there are any zeros or roots of the rational function. And then typically you pick a few points between the zeros, the intercepts, and the asymptotes, and those help guide your graph. So we'll just do these two for a good example. So x squared minus x over x minus 1. So this one may look familiar. So denominator of f is already factored, so we know that our domain is going to be from negative infinity to 1, union from 1 to infinity. So we factor the numerator to see if there are any common factors. So we have f of x equals x squared minus x minus 1. And like before, factor out an x, and that just leaves you with f of x equals x. So x equals 1 has there is a hole at x equals 1. Specifically, we now have to figure out what's the value of the hole. So I guess instead of I should say at x equals 1, because that implies a whole vertical line, there's a hole when x equals 1. So to figure that out, we just plug in. So if f of x has reduced to x, then f of 1 equals 1. So there's a hole at the point 1, 1. So to figure that point out, or to figure out what where the hole occurs, you just plug it into the reduced equation. So what does that look like on a graph? Well, y equals x, that one's pretty easy to graph. So then if we just graph it as normal, but we have our open dot here to indicate that this is a hole, which means this function goes along y equals x, all things as normal, and then when you get to 1, 1, you jump over it, and then you continue on with life as usual. Now, this one's a little bit more interesting. So if we factor this, so x squared plus 1 divided by, like I said, these are familiar. What multiplies to get negative 15 and adds to get 2? Negative 3 and 5. So I get x minus 3 and x plus 5. So this means that we exclude negative 5 and 3. So our domain is negative infinity to negative 5, union negative 5 to 3, union 3 to infinity. So now we check and see, all right, x squared plus 1, that won't factor. It will factor, but it'll have imaginary parts, and we want to avoid that if possible. That means that x equals negative 5 and 3 will be your vertical asymptotes. So next we need to determine our horizontal asymptotes. So now we have to determine the or if there are any horizontal or oblique asymptotes, or if there are none. So like before, these are both the same power. So that means your horizontal asymptote is y equals 1, because it's 1 divided by 1, which gives us a nice outline of the graph. Now also what this has done is it's created this partition for the function g of x, because remember we said it can cross the horizontal asymptote sometimes. The question is going to be, which boxes does this fit in? Because you have, could something go here, 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 or here. This is why the plugging in of points is very important. So if you plug in 0, we get that our y-intercept is 0, negative 15. And also, interestingly enough, if we set the function equal to 0, there's no x-intercepts. So if you plot a few points in each region, and typically you define a region by, is it between two vertical asymptotes, or is it to the left or right of two vertical asymptotes? And once you do that, you would get a graph that looks something like this. So, like for this one, you would probably want to pick, so let's see. This is negative 5, so 1, 2, 3, 4, 5. Pick points like negative 6 and negative 7. And then once you know that it's kind of doing this, you know, okay, well, I've got to stay in this little sector, so that gives you some guidance. Now, to figure out if the function crosses, because this is something we didn't talk about, how do I know if it crosses the x or the horizontal asymptote? Well, you set the function equal to it. So does x squared plus 1 over x squared plus 2x minus 15 equal 1? And so if you multiply both sides by the denominator, you get x squared plus 1 equals x squared plus 2x minus 15. And to simplify a little bit of all this, I'll move everything over to one side, and that's going to give me 0 is equal to 2x minus 16. Simplifying a little bit more, this means that when x is equal to 8, so yes, so it crosses the HA at x equals 8. Which means if I plug in 8, this function value will come out to be 1. So that will give you an idea, because it'll go down, but then it'll come back towards that. So whenever you're checking to see does it cross the vertical asymptote or horizontal asymptote, never crosses vertical, you just set it equal to it. That's all you have to do. And that covers it for rational functions. Next thing we'll pick up on is the trig section, and then with the trig section we will have covered everything for the course, so we're slowly approaching the end.